Okay, so welcome to this session about SE for AI. So we have very nice presentations, and most of the presenters already talked to me, but we are still missing some presenters. So if you are a presenter and didn't talk to me, please just come to see me. We'll be starting by the first presentation, a test oracle for reinforcement learning software based on Lyapunov stability control theory. And the talk will be presented by Qixin Wang.
Qixin Wang.
Yeah.
Okay. Hello, everyone.
Have like 10, 11 minutes.
Huh?
10, 11 minutes.
Oh, okay. Right. Okay. Hello, everyone. I'm Qixin Wang from the Hong Kong Polytechnic University. Today, I'm going to present my paper with my students and my colleagues. So we all know that reinforcement learning is becoming more and more important because of its ability to train controllers for complex systems and robotics, particularly those systems that are too complex to be analyzed using conventional control theories. Typically, the reinforcement learning framework consists of two parts. One part is the environment. Intuitively, it is the physical plant being controlled. It takes as input the control actuation, also called action, and the state of the environment will evolve accordingly. On top of the environment, there usually is a piece of software called interpreter that monitors the state of the environment and also evaluates the current state as well as evaluating the impact of the action. So the result is called the reward. The other part of the framework is the reinforcement learning program. It takes as input the reward and the state of the environment to train an agent, aka the controller. The controller is in charge of making decisions, the actuation decisions, aka the actions, to be fed back to the environment. So at a higher level, the ultimate output of the reinforcement learning program is the agent, the controller, and the environment is the input to the IO program. Sometimes the environment is also replaced by the so-called digital twin or simulator, so that the entire environment will go cyber. So in this way, you can run the environment millions of times without wearing down the plants. As reinforcement learning generated controllers are being used for many safety critical and mission critical applications, such as surgeries, smart vehicles, nursing, robotics. So the guaranteeing the correctness of reinforcement learning is becoming more and more important. That means we need to do testing. We need to do debugging on reinforcement learning programs. To do testing and debugging, we need a special tool called Oracle. This is a tool that looks at the input of the software and output of the software, and merely based on these two, it can judge whether or not the software is buggy or not. Okay, so the Oracle design problem or Oracle problem is already difficult for conventional software. For reinforcement learning software, the problem becomes even more difficult. This is because in conventional software, given a piece of input, the output is unique and deterministic. But for reinforcement learning, the output is not unique usually. Okay? Remember, the ultimate output of reinforcement learning in the control context are the controllers. But for the same control task, there could be different ways to control. For example, I want the controller to fly a quadcopter from point A to point B. So we have one controller fly this way, the dotted line trajectory. The other controller fly this way, the dashed line trajectory. So which trajectory is buggy? Which one is not buggy? Okay, it's very difficult to define. Because of this, how to design oracles for reinforcement learning, it's very difficult. So when we thought about this problem, we feel that we need to go back to the root. That is the domain knowledge in control theories. You need to look into the control theories to design the oracles for reinforcement learning. So our heuristics is that in control theories, there are many well-defined control problems. and they have very, very well-defined solutions, analytical or numerical solutions. And these solutions, they already have certain features. So if our conjecture is that if the reinforcement learning generated controllers most often agree with the well-known solutions features, then most likely this reinforcement learning program is bugless, is correct. Okay? Otherwise, it could be buggy. So this is our conjecture. So specifically, the control theory that we look at is the very famous Lyapunov stable controller design theory. So this set of theory, it looks at linear control systems describable by linear differential equations like this. Okay? So X is the state of the, sorry, the laser is not working. The X is the state of the environment. Usually it is a n-dimensional vector. And then U is the control input into the environment. Usually it is an m-dimensional vector. And then how the X will evolve, the derivative of X over time, how X will evolve is determined by the current state of the environment, aka the plant, and by the control input. And the relationship is a linear relationship. Here, A and B are both constant matrices. So the design objective is that we want a linear controller. The control signal should be also linearly related to the current state, so that the holistic system will be stable in the sense of Lyapunov. So what is the stable in the sense of Lyapunov? Basically that in the vector state space, like Rn, in this vector space, we can find a region. Typically, this is a hyperellipsoid region. And starting from any state within this region, the future trajectory of the state will never exceed this region. So it's a sandbox. Okay? So there is very well-established theories on designing linear controllers systems that are stable in Lyapunov sense. The key to the design is first you need to construct a hidden function called the Lyapunov potential energy function, like V. It's a function of the state X. So what is Lyapunov potential energy? So this diagram illustrates the idea. So suppose we have a two-dimensional state space, X1, X2, two-dimensional X. And then on top of this state space, we define a Lyapunov potential energy. Typically, it's the shape of a bowl-shaped surface. Okay? And then starting from any initial state, there is an initial Lyapunov potential energy. And then the trick is that if over the time, you can guarantee the Lyapunov potential energy always decrease, then correspondingly, the trajectory of the state space will always be confined by this ellipsoid shape, which is actually the projection of the contour of the initial Lyapunov potential energy. Okay, so I have all these theories. So in summary, there's already a very well-known numerical solution for this Lyapunov stable controller design problem. And then the feature of the solution is that the so-designed controller U will always decrease the plant's Lyapunov potential energy over time. Okay, that's the key feature. So corresponding to this background knowledge, we propose our reinforcement learning oracle like this. We conjecture a correct reinforcement learning program can figure out the hidden Lyapunov potential energy concept and the energy decrease feature. Okay? So first, we randomly generate many non-trivial Lyapunov stable controller design problems. This is easy. Basically, you randomly generate this A matrix and B matrix. Okay? You generate A and B, then you generate a Lyapunov stable controller design problem. And then we can apply the conventional, very well-established Lyapunov designer theories to prepare the ground truth Lyapunov stable controller U and the Lyapunov potential energy V functions, okay, according to the conventional numerical solutions. And then during the reinforcement learning training stage, we use the ground truth Lyapunov potential energy V, its decreasing feature, okay, to stimulate the reinforcement learning, to generate the reward, basically. So if it follows this rule of decreasing potential energy, then we reward it. Otherwise, we'll punish it. Okay? So our conjecture is that if the reinforcement learning program is correct and smart, it will figure out this hidden function of V and the hidden rule that V should be always decreasing. So in the testing stage, we check if the reinforcement learning generated controller complies with the ground truth Lyapunov potential energy decreasing feature or not. So how to judge whether it complies or not? So the rule is that first, an reinforcement learning generated controller is considered to be complying if and only if over var theta percentage of its tested control steps are Lyapunov potential energy decreasing. And then second is that the RL program is considered bugless if and only if over theta percentage of its generated controllers are complying. So therefore, this is our so-called Lyapunov potential energy abnormality oracle, or LiPA oracle. It has two configurable configuration parameters, var theta and theta. So how to judge whether this oracle works or not? We have to do empirical study. So what we do is that we find a very well-established repository implementation of the reinforcement learning programs. It's called the stable baseline repository. And then from this repository, we assume that the most up-to-date version is bugless. So from them, we select the most representative implementations for classic reinforcement learning algorithms like A2C, PPO, TD3. These are classic reinforcement learning programs, algorithms. So we generated a benchmark of bugless programs, reinforcement learning programs. And then on this benchmark, we inject bugs. We have two categories of bugs. One is the artificial bugs. So there is a very famous survey on the reinforcement learning software bug types. Okay, so this is an artificial bug, and the other one is the real bug from the real world, the real repository logs. And then we have these two benchmarks, the buggy programs and the bugless programs. And then we threw these programs to our oracle to see the result. And in comparison, we also use human oracle, which basically means that we assemble as human experts as a team to label, to judge whether programs are buggy or not, to compare. And this is the comparison results. The x-axis is the different kinds of oracles that we use. HO means human oracle. And then these are the different configurations of LiPA oracles. And then we compare accuracy, precision, recall, F1 score. So we see that most of the LiPA oracles, they can outperform the human oracles in most metrics, particularly LiPA oracle with var theta equal to 100%, theta equal to 75%. It significantly outperforms the human oracle. And then we also compare false positive rate, false negative rate. The smaller, the better. We can also see that LiPA 100%, 75% is better than the human oracle. For true positive rate and true negative rate, the bigger the better. We can also see that LiPA 100%, 75% is much better than the human oracle. And then this is the ROC lines comparisons. The x-axis is the false positive rate, y-axis is the true positive rate. The curve, the bigger area underneath the curve, the better. So we can see that the overall, our LiPA, this one, the red dotted line is the LiPA. 100% is 75% is much better than the human oracle, which is the black dotted line. And then conclusion is that our oracle works, and particularly the 100%, 75% outperforms human oracle significantly. Thank you.
Thank you. So we have time for 2 questions, and please, the second presenter, just set up your presentation. Yeah.
And also, sorry, I assume that the theta and the theta, they balance each other, right? So you cannot have 100%, 100%. You did a study of sensitivity to see what happens.
Yeah. So
because 25% means if in one out of 4 is wrong, right?
Yeah, 25% means that one of the 4 steps is not like var theta.
Yeah, one out of 4 of the oracle or controllers are not complying, right?
Yeah.
So, and can you make it 0, or otherwise you have to drop the theta? So can you tell us something on 2 parameters?
How do they interact?
Yes.
We do not have a theory on how to optimally configure these var theta and theta. So what we do is brute force. We try all the possible configurations. So here you can see that in our comparisons, the var theta value, we have 4 values, 100%, 97.5%, 95%, and 92.5%, 4 configuration values. And the theta is 75, 50, 25, and 100, yeah, three values. Theta, we have 3 values. So we try all these combinations and see which one is the best combination.
Unfortunately, we don't have time for another question. So we will, let's thank the speaker.
Thank you.
And I forgot to mention that this is a award-winning paper, so congratulations.
Thank you. Thank you very much.
So the next